Thank you for introduction. I'm Junji Seino from Waseda University in Japan. First of all, I'd like to thank giving me an opportunity. First of all, I will thank organizer for giving me an opportunity to talk here. So my presentation title is Construction of Orbital-free DFT Scheme and its Evaluation by Machine Learning. And this is the content of my talk. First, I will talk about the introduction of my presentations. Then, I will explain the development of kinetic energy, functional, machine-learned electron correlation model, and its evaluation of using the machine learning scheme. So in density functional theory, the electronic energy is expressed as the function of electron density like here, and these components, kinetic energy, interaction between external field and electrons, Coulomb repulsion, exchange, and correlation energies. Some of these have an exact expression, but exact expression are unknown for T, Ex, and Ec. So first, I will focus on the kinetic energy T. The absolute value is larger than these two energies. So here is a history of development of kinetic energy in DFT. And in last 100 years, several functions have been developed so far, and however, the mainstream to calculate the kinetic energy is based on the Kohn Sham DFT, because this gives a practical accurate kinetic energy. And this is an expression, and by introducing the orbital. The reason why is the accuracy of OF-DFT is low. So here is the equilibrium bond distances for these diatomic molecules. The KEDFs in blue reproduces experimental value in black. However, OF-DFT in red have a very large deviation from experimental value or KEDFs. The largest value is about 0.4 angstrom. So more accurate kinetic energy functional is essential. However, the OF-DFT has big advantages. This scheme is much faster than KEDFT. This figure shows the computational time for these aluminum atoms. This OF-DFT can calculate the large number of aluminum atoms. So when accurate OF-DFT is developed, the paradigm shift from KEDFT to OF-DFT will occur. So let's move to the theoretical aspect of kinetic energy density functionals. This kinetic energy functionals is classified into three, like here. First one is local kinetic energy density functional, which includes only electron density. The total kinetic energy is approximated by the integration of kinetic energy density. And the second is semi-local KEDF, which includes electron density and derivatives. Third one is a non-local kinetic energy functional, which includes information of different position of electron density to consider the non-local effect. So in this presentation, we focus on this semi-local KEDF. And in conventional semi-local functionals, the explicit expression is constructed to satisfy physical conditions. For example, Thomas Fermi functional is exact in homogeneous electron gas, and the von Weizsäcker functional is exact in one-orbital systems. Depressed Kress reproduces the trend of electron gradient with many parameters. These parameters are optimized to reproduce experimental or more accurate calculations. And the Becke functionals have the same expression to exchange correlation functional with the different parameters. And the fourth-order gradient expansion approximation uses the second-order gradient of electron density. However, the recent functionals with many parameters tend to give large error in local properties such as electron density. And this figure shows the electron density error. Horizontal axis shows the error the functional developed. And before 2000, the error decreased like here because the functional is constructed to satisfy the physical conditions. And after 2000, the error increased like here because the functionals have the many parameters. In order to estimate the functional with the many parameters, the machine learning schemes is very useful. And here is an example for construction by machine learning of implicit, semi-local, and non-local expression using electron densities. These schemes shows the calculated bond dissociation of diatomic molecules, potential energy curve for hydrocarbon, and the kinetic energy density for metals and molecules. And here is an example of potential energy curve for C2H6 molecules by using the convolutional neural network. So from this result, the neural network schemes gives almost same lowest energies, a position of lowest energies, but the curve is not smooth. So we have also developed semi-local machine-learned kinetic energy density functionals. And here is the procedure. First, we calculate molecules and to obtain the electron density and kinetic energy density at each grid point with a small space. And we construct the relationship between the descriptors and the objective variables. We can get functional. And here is a detail in machine learning, and we use neural network architecture like here, and computational detail is like here. We have used three layer for hidden layer and 30 nodes. And for descriptors, we use electron density and its derivatives with up to third order based on gradient expansion approximation. And for objective variables, Kohn Sham kinetic energy density, written like here, was used, and the notation of this model is defined like ML n, and this n means the order of gradient. And this is a training set. we use 2% of grid points for 19 molecules in GDB9 dataset. The total number of grid points is about 100,000. And let's move to the result of accuracy of energy. This figure shows the mean absolute deviation from KEDFs reference value, and the horizontal axis shows the conventional and the present functionals. And these functionals contain electron density, first, second, and third order gradient. And from this result, this ML3 machine learning schemes gives the smallest deviation. The value is 0.065 Hartley. And here is the kinetic energy density map in water molecules. And this is a result for conventional SE94, present ML3, and KEDFs reference values. And these conventional schemes gives large deviation from the reference value like here, especially in core and the bonding region. However, this present schemes gives almost same density map. So this machine learning schemes reproduces behavior of KEDFs in core and the bonding region. Finally, this is a result of potential energy curve in typical small molecules, CO, N2, HF, and H2O. And this machine learning schemes reproduces a curve of Kohn Sham DFT, like here, with a small smooth curve. So next topic is to develop the machine-learned electron correlation model to predict the accurate electron correlation. In order to estimate exchange and correlation energies, in DFT, we calculate energy as a function of electron density, and the accuracy depends on functional form, like LDA, GGA, meta-GGA, and hybrid GGA. However, the accuracy is not systematic. In wave function theory, whose energies are also calculated using virtual molecular orbitals, and the accuracy is systematically improved. If we use accurate theory and the large basis set, we can get the accurate result. And here is an example of electronic energy, enthalpy, and free energy of formation in water molecules. These are calculated by using the Hartley-Fock, MP2, CCSD parenthesis T, and the DFT. And the horizontal axis shows the basis set. So if we use the accurate schemes, like a CCSD parenthesis T with a large basis set, the result is very close to the experimental one, within 0.4 kilocalorie per mole. So in wave function theory, in order to estimate complete basis set limit, we normally use these two schemes. One is to use the extrapolation, which fits the convergence of the correlation energy with the appropriate function, like here. And the second one is composite method, which reproduces the CBS limit by combining result from lower calculation level, written like here. So by using these concepts, we have developed a low-cost and highly accurate electron correlation model by machine learning. The system is same as that you in kinetic energy functionals. So for descriptors, we adapted electron density, gradient, kinetic energy density, Hartree-Fock exchange energy density, and non-integer orbital occupation for electron densities. And for objective variables, we use the correlation energy density calculated with CCSD parenthesis D with CBS limit. And this is the condition in machine learning. For training set, we use 15 small molecules containing H, C, and O atoms. And these geometries are optimized by using these DFT functionals. And for learning data, we adapted about 30,000 points of correlation energy density. And this is about 1% of all grids point. And this is a testing set. 33 small molecules not used for learning used. And here is a type of chemical bond for training and testing. And this is a result of prediction of correlation energies. The horizontal axis shows the deviation from reference schemes, this one, and these are results by using the combination of several wave function theory and the basis set. And from this result, machine learning schemes gives almost the same values of the reference schemes. And we apply these schemes to reaction energies. We use these 12 chemical reaction energies, including hydrogenation and dehydration. And this yellow means molecules not used for learning. And this is a result for reaction energies. We compared with the conventional 73 functionals, and the reference is this level. And from this figure, this MLEC can calculate with an accuracy of less than 1 kilocalorie per mole, and with higher precision than this DFT. And here is the computational cost of this method. And the wall time, this figure shows this wall time to calculate total correlation energy of CH4 molecules. And we compared with the method for estimating these reference values. And if we use the extrapolation schemes, the computational cost is about 17,000 seconds. And this composite method requires about 300 seconds. On the other hand, this MLEC schemes needs about 50 seconds. And the time-consuming step of these schemes is calculations of descriptors. And if we use parallel computing, this time will be reduced. So let's move to the final topic, evaluation of quantum chemical schemes using machine learning. And we have developed the two schemes. First one is introduction of applicability domain, and the second one is to perform atomic clustering considering surrounding environment. And the first one is to introduction of applicability domain, which provides confidence in unlearned data by determining whether data to be predictable. If the testing data is in applicability domain, the error will be close to the data neighboring data. So here is a scheme to determine applicability domain. We have used the jackknife aggregation method, jagging method, which is one of the methods based on ensemble learning. And this method constructs submodel by combination of different descriptors, and we determine AD from standard deviation between these submodels. The data point with large standard deviation value is determined as outside of AD. And this is a result of spatial distribution of data point outside of AD. And these are case with a lot of data points outside of ADs. And this red shows the data point outside of AD, and the molecules with unround element, interaction, intermolecular region, charged molecules, and variation of bond length like stretching or rotation have large number of data points outside of AD. So this, we applied these schemes to MLEC models. This table shows this mean absolute error of data points inside or outside of AD for these systems. This MAE inside of AD less than 1.5. However, the MAE outside of AD is maximum, the maximum value is about 200. So MAE of data points outside of AD is larger than that inside of AD. Okay, this is a second schemes, atomic clustering considering surrounding environment. So the objective of these schemes is to estimate accuracy at levels that are interpretable by human. So we have developed a classification method of atom in molecule based on machine learning clustering. And we apply these schemes to accuracy of molecular properties like carbon-30 NMR chemical shift. And this is a data set and clustering. We randomly selected 5,000 molecules, included about 30,000 carbon atoms from QM9 data set. And for clustering, we use density-based spatial clustering of application with noise, a dB scan method. And we use two types of descriptors for clustering. First one is structural descriptors, which is based on weighted atom-centered symmetry functions. And the number of descriptors is about 3,000. And the second one is electronic descriptors for these properties. These are calculated by the quantum chemical calculation. And we perform the dimensional reduction of descriptors for clustering based on these conditions, and we get these 4 descriptors for clustering. And this is a result of clustering of carbon atoms. We obtained 36 clustering, and this table shows this cluster ID and the qualitative characteristics for each cluster. And this includes primary, secondary, tertiary, quaternary carbon, and C2 and sp2 and sp carbons, and so on. And these results are consistent with our intuitions. So this scheme is applied to the evaluation of NMR chemical shift. And we have used the 84 DFT functionals, and the reference is MP2. And this is a heat map plotting mean error from MP2, and the horizontal shows these functionals, and the vertical axis shows the functional, and the horizontal shows the cluster numbers. And if we use the same functionals, the deviation depends on cluster, like here. So atomic statistical data does not make a lot of sense. So finally, I will show you the box and the whisker plot for these 3 functionals. And from these results, if we use the same chemical species like sp2, the error differ among the cluster. For example, the maximum value is about 10 ppm from here to here, here to here, and here to here. Okay, this is a summary of my talk. We developed the semi-local kinetic energy functionals for accurate calculation for the OF-DFT. And we also developed to predict the accurate correlation energies. And we have also developed two evaluation schemes based on machine learning. And the machine learning scheme is very useful tool to accurate and efficient calculation based on quantum chemical theories. And I acknowledge collaborator and research grants. And thank you very much for kind attention.
Questions?
Thank you for this nice talk. Can you go back? You had a slide where you showed dissociation curves of molecules in the part where you learned the kinetic energy functional. Yeah, this one.
This one.
Ah. So in the last curve, the other curves, they fit very well. In the last curve, there is a deviation when it comes to larger distances. Can you comment on this?
Yes. Okay. In these schemes, we use electron density and its gradient, and distance between atoms. This means considering atoms. But in order to calculate like water molecules, we have to consider the like a angle and so on to describe the non-interacting effect. So I think this is this result have some lags for descriptors.
Thank you.
I'm very impressed by this, and in particular, I like that you got rid of the basis set problem and teaching it up to complete basis set. But as somebody said before, the machine learning can never be better than the underlying theoretical model. Now, I like to be a chemist, and I like to break bonds and do dynamics. And in that respect, neither coupled cluster nor Kohn Sham DFT would help me much. How do you see us proceed in doing wave function theory with machine learning where I can break the bonds and actually get the full CI result?
I think it's a different difficult questions. So if we use the appropriate descriptors for like a bond, yes, for description of bond dissociations, we can describe the, we can predict the error between CCSD, from CCSD to full CI, but yeah,
But usually when you do these dissociation curves, the coupled cluster makes a strange quirk.
Yeah.
And also they have an inability to get the transition state correctly. And I mean, getting the activation energy, if you're interested in the chemical reactivity, is essential. I mean, I would like to see these kind of methods be the one we explore, like the chemistry that Marcus was talking about. And in that respect, we need machine learning techniques to produce full CI results rather than coupled cluster. I hope you agree.
Yes, I want to use the full CI schemes for this method. Yeah, thank you.
Okay, so let's thank the speaker once more. Thank you.